Am I audible to everyone?
Yes, sir.
Okay.
Yes, sir.
Is my screen visible?
Yes, sir.
Okay. So now you can see here the heading is the floating point arithmetic, and here in the general system, in the generalized form, some machines or some systems take this type of floating point numbers. Actually, this x equal to plus minus 0 point some d1 d2 dn of beta. So this beta is the actually base, and where this d1 d2 dn are the numbers of all digits. That means if it is a binary system, so it have a 0 1, and if it is a decimal system, so it may be from 0 to 9s, any number may be theirs. So and here the normalized form is actually denoted by this type of form, that 0 point d1 d2 dn is said to be normalized if this d1 is not equal to 0. That means that if this first number is a not equal to 0 number. So that is another type of format. So not like the general binary format. So here in the normalized case, they are saying that 0 point this is the normalized form, and where this is a non-zero format. Non-zero format means it may be 1 or it may be 0. Not 0, it may be 1. If it is a decimal, it may be 1 2 3 4 5 6 7 8 or 9, maybe any numbers, but it is not a 0 number. That means if you take that 0.04678 and e2, that means exponent 2 or exponent minus 2, this is not a normalized number. If you want to make it normalized, then it will be 0 point, then you have to shift this point from here to here, and it will be 0.4678, and since you have taken in the right hand side, this e will be reduced by what, 1. So that means you can take also this type of format for the normalized expression. Now the question is, if suppose your normalized format looks like that 0.4253 and e8, that means after the 0 you have a number, and this is a decimal system, not a binary system, then how you will calculate how you will take the summation, how you will take the subtractions, and how you will make the multiplications or divisions or any other things. That is another thing, the how computer actually calculate all of these things. So here you have some rules, and the rules are like that. So first of all, the addition of a normalized floating point number, and where the normalized floating points suppose only have taken the 4 digits in the mantissa part. So in the 4 digit mantissa parts, there are two numbers. One is suppose 0 point, here you can see 0.7642, this is one number, and another number is 0.4253. But here it is a e4, that means exponent 4, and it is a exponent 6 system. So before adding these two numbers, you have to convert both with the same exponent, otherwise you can take the summations. So we have shifted, so it is e6 and it is what, e4. So we made both the number in the e6, that means in the largest power. So whenever you make it, what you will get? You will get 0.0076, because you are just, this is 0.7642 and e of 4 mean exponent 4, but we need exponent 6. So whenever you make it exponent 6, that means you are taking a divisions by e2. So your point will be shifted 2 steps in the left hand side, that means it will be 0.007642. But the problem is your machine can only store 4 mantissa point, so that means then it will neglect this 4 and 2. So now this is 0.0076 e6, that is the problem. So if your machine can hold more points in the mantissa, so in that case your error will be less, but otherwise it will cut like this, because it can only take these 4 digits, not more than, so it will truncate the numbers after the 6 and it will only take 0.007 and 6. So first of all, you have to make the exponents equal by shifting the mantissa, that is the first things, and make both term with the same exponents, and if possible make it with the largest exponents. So then it will be 0.0076 E6 and 0.4253 E6, and then it will be 0.4329 E6. What happen if you make it E4? This question may arise in your mind, because in that case this term 42 will not truncate. But the problem is, whenever you make it E4, that means 0.4253 E6, and whenever you shift the point from here to here, then it will be what? E4. And it means it is not normalized number, because in the normalized number we are saying that in the left hand side there is only 0, but here you have 42.53 into E4, and now this is not a normalized number, and that means you can't use the additions method here. So that's why, since it is in the normalized form with the E6, but if you make it like that 0.0076, in that case you may use it for the summation, not normalized, but you can make it for the summation, and that is the summation process, and after making that you have 0.4329 into E6. That is the process. Same method for the subtractions. Here, if possible, make it with the smallest exponents. That means here, suppose E minus 5 is there and minus 4 is there, so what is bigger? This minus 4 is bigger. So first make every exponents with the form of minus 4. After that make the subtractions. So always which is bigger exponents, just make it first and then take the subtractions or additions or anything else. So here, like if you want to subtract these two number 0.4673 E minus 4 and from 0.8542 E minus 5, that means from this number you want to subtract this number. The smallest exponent is e to the power minus 5. So we increase the exponent by 1 to make it same as minus 4, and then just shift the point 1 in the left hand positions and you will get 0.0854 and e to the power minus 4. Now subtract it. Not that actually this is equal to, here I think they are doing it wrong, that subtract this from that number, but here they are subtracting this number from that. That means this number will be 0. This is less number actually, so that will be 0.7643 e to the power minus 4. So this language will be actually wrong here. So language will be, I think, subtract 0.8542 e minus 5 and from 0.4673 e minus 4, and otherwise you have to take one negative signs here if you take the subtraction like this. So that is the general method for addition. So that means first make every exponent same, and by approximating or by changing all the exponents to the highest exponents available there, and after that add it or subtract it. That is the process. In the multiplication process there is no such type of actually restriction there. Whatever may be the numbers, just make it normalized and after that just multiply it. So here the multiplications pattern will be like that, multiply the mantissa and then multiply the exponent and exponents. So suppose you want to multiply these two numbers, that 0.5634 E11 and 0.1532 E minus 14, then simply the calculations method what you have already used in the throughout or up to now, that if you want to multiply 0.35 into 10 to the power minus 2 and 0.76 into 10 to the power 4, then what you will do, just multiply these two number and there will be 10 to the power 4 minus 2, that means add the powers. So here also be the same method, just multiply mantissa and then exponent into exponent, and whenever you multiply the exponent into exponent, so here you have to take the additions of the exponents. So that means here you will get 0.5634 into 0.1532, it will be a big number 0.08631288, and after that E11 into E minus 14, this two number gives you E minus 3. So your number is actually 0.08631288 E minus 3, but here the mantissa have a 4-digit format. So first of all make it normalized. So whenever you make it normalized, you have to shift it 1 in the right hand side, so it will be reduced by 1 digit, that means it will be 0.863128 into E minus 4, and after making that you can neglect the 1 2 3 4 after that digits. Your system will neglect all these values and it will give 8631 and E minus 4, because it have a 4 mantissa format only. So that's why it will gives you 8631 and E minus 4, that is the value. Similar pattern follows for the division also. So in the division also, just divide the mantissa and then divide the exponent, and in the division you will get the minus of the power of the exponents. Like here these two numbers are 0.222000 and 0.8883. So these two numbers after divisions gives you this type of value 0.2251, and if more values are there, so since you have a 4-digit mantissa, so it will neglect all the values and it have a E2. So that is the values. So now if you have any doubt you may ask, because after that there are some examples, not anything else. So that is the patterns how machines actually evaluate the values. So that means every time you will use the multiplications or divisions, so actually you are neglecting the values, you are truncating the values, you are chopping the values. So that's why here if you can reduce the steps made by the machine, so then you will get actually the more accurate value. That means sometimes if you calculate the x square minus y square by suppose x plus y, rather than it is actually good to calculate only x minus what? Y. Because you know that after giving the formula, if your x plus y not equal to 0, then this is x minus y into x plus y, and after one step you have what? X minus y. So now suppose someone is using this formula is equal to some fxy function, and someone is using suppose fxy is equal to that values. And now if you have a less precision machine, suppose not a high precision machine, in high precision machines it is a negligible error, but if your machine is not so much good or very less precise machines like the calculators or anything else, so in that case it will truncate the values, because what is the calculation method here? Here it first calculate the x square, so whenever it calculate x square it will truncate some digit, then it will calculate y square, again it will truncate some digit, after that it will calculate the x plus y, maybe there is no truncation, but again you will divide it by x plus y, again it will truncate the digits. So that means there are 3 steps where the truncation or the chopping may occur. So that means your number or the accuracy may compromise here. So we will analyze one actually case here like this, and that is also important, but that is the pattern or that is the rule for calculations. If you have any doubt, you may ask, or otherwise we may go to some problems. Have you any doubt?
No, sir.
Okay, so then here is one very simple problem. Multiply the following floating point numbers. Two numbers are there, and now you all know how to multiply it. Just multiply the mantissa and just add the exponent. At the adding exponent you will get 25, multiplying mantissa you will get 0.026184746, but this is not a normalized form. To make it normalized, shift the point 1 by 1 actually positions in the right hand side, and you will get 0.2610, and it will be reduced by 24 because you are shifting in the right hand side, so it will be reduced by 1. Now your machine will truncate the numbers after that 8 because and retaining the 8 digits in mantissa, and after that it will truncate everything, and you have that 0.2618 and E24. This is the numbers. So that is the way how the machines actually calculate. And there are also one questions, and you can just see it. Apply the procedure, the following multiplications. There are also two 4-digit numbers, and there is some multiplications. So just see it as your homework. I think you will understood the process. Now take another important example, which is example 3. I have already said that take two values, suppose x equal to that and y is equal to that values, and calculate the values of x square minus y square by x plus y using the normalized floating point arithmetic, and compare it with the value of x minus y and indicate the error in the format. If there is any error, maybe absolute error, maybe relative error, or maybe percentage error, that means what is the difference between these two values. So you may get some different values, or you may not. Basically in this type of small format system, 4 mantissa or such type of system, error occur, but in particular type of problem error may not occur. So what is the solution? So you have x, first you calculate x square, or you can calculate x plus y and x minus y also. So what is x plus y? So simply 0.8454 means 0.8454 E0, and it is also E0, both have no exponents. So x plus y will be simply the sum of these two, but whenever you take the sum of these two, it will be after the summation you can see it will be 1.6854. Now this is not a normalized form, so to make it normalized you have to shift this point in the left hand side, so it will be increased by 1. So that means it is 0.16854 E1. Now the problem occurs actually after making that. Now it have a 5-point mantissa, but retaining the 4 digit, it will truncate or chop it from here, and it will gives you 0.1685 and exponent 1. That is the final values. And what is the x minus y? So in the x minus y, so it will be 0.8454 and minus 0.8400 E0. After the subtraction you have 0.0054 E0. Now in the final saving, this 00 is not acceptable in the normalized form, because in the normalized form after the point you have a non-zero values, so it will shift the point from here to there before the 5. So that's why it will be again actually reduced by 2. So 0.54 and these two blank space will be filled by 0 and E minus 2. So that is the normalized form for x minus y. After that, so we have now x minus y values and x plus y values. Now we calculate x square minus y square. So here x square is equal to x into x, that means 0.8454 into 0.8454. After the multiplication it will be 71470116 E0. Now this is a normalized form, so it will just truncate after the 4 digit, so it will truncate that values, all these values, and after that you have only 0.7147 and E0. So this is the value of x square. Similarly calculate the y square values. So y square will be again after the truncations. So here no truncation is actually needed, because 84 into 84 will be 7056, and after that all zeros are only there, so it will be 0.7056. Then calculate the subtractions, x square minus y square. So it will be 7147 and it will be 0.7056. So that means 0.0091 is 0. So again it will shift the point from here to there and it will be 0.9100 and exponent is minus 2. So now calculate the division. So x square minus y square by x plus y. So it will be 0.9100 e minus 2 and 0.1685 e1. So after the calculation, so our integer division, you may get 5.4005937 and e minus 3. Now since you have to shift the point from here to before the 5, so you will get 0.5400, it will be 0.54005937 and e of minus 2. Now fortunately you have 2 0 after the 5 4, so that's why after the truncations also in that machines, so 0.5400 into e minus 2 and retaining the 4 digit, that is the value, and this value is actually same as the previous values. So that's why here the relative error will be 0, because if you see the x minus y value in the previous page, it will be also same 0.5400 e minus 2, and in that machines also 0.5400 e minus 2, and here for this machine these two values are same. So relative error will be the value of x minus y minus value of the second expressions by value of the x minus y, which we have taken as the original value or good values actually. But for this case, for these numbers, the relative error will be 0. But it is, you can't say that for any number this value will be 0 always. So you can take any two other numbers. Let's just, you can take this type of values only. For suppose x equal to, just take these values 0.1738 and y is equal to 0.2505 as your just homework. Just take these values as x, it will be better, and this value is x, so take it as y and just do it in your home, that for these two numbers is there any error or not. Maybe there is some error, okay. But now you understood that how the truncations actually happen. So that's why if you use more steps, so there is a possibility of neglecting more digits or precise values, and which will produce the error, okay. So in the example 4 also there is one such type of problem. So a e value is given and value of e to the power x, you all know the series, that is the series form, and if you want to calculate the x values, e to the power x values at that point, suppose 0.2505 e1 point, so then the machine will calculate it by using the series, and that is the actual value of e, or up to actually 4 decimal places. Now if you calculate the e, then e square, that means using the normalized floating point arithmetic, then suppose that values, and in this way just produce the values and the e value is given. Now again you can check is there any error or not. Here they are calculating some particular values, but you can again check also here that what is the value of e to the power x by using the normalized arithmetic, and what is the difference between the original data and the data you have calculated through this machine.